Everybody, I'm Siqi Shen from Delft University of Technology. Today I'm going to talk about modeling avatar mobility in network virtual environments. If you were in the non-stop session, you will probably listen to my talk about understanding the mobility patterns in virtual world and also compare it with the real world GPS traces. But in this world, we only focus on the avatar, how to model avatar mobility traces, how to generate the mobility traces. This is different kind of topic. And why we want to do this work? Firstly, there are two major ways to provide input for evaluations of network virtual environments. Either you use the real-world traces from some game, or you use some mobility model to generate some kind of traces. But using the real-world traces, it has one advantage of using real-world traces. It is the credibility. It is real, and then you can say that and if you use the traces, and then you can say that our method apply in this kind of game. But the problems of using real traces is the flexibility problem. You can only say that if I use the traces from my class, and then we can say the approach applies to the other games, such as Second Life. And yeah, the second approach is using mobility model. But mobility model, the problem mobility model is the advantage of mobility model is the flexibility. It's very easy to generate large scale traces, but the disadvantage of mobility traces or mobility model is that they may not well capture the mobility models. They may well capture the mobility characteristics we are focused on. So in this work, we are trying to generate large scale and realistic avatar traces. First, I will talk about our work with the data set we use, and then I will talk about how we model each mobility patterns separately, and then we will use a sum over to combine all the mobility properties to generate the traces, and then we discuss the limitation and then the conclusion of the work. Data set. We basically use one data set we use is cloud. We collect from Volvo from Iron Forge, and the second data set we collect is from we get from Yang et al. From National University of Singapore, from Brady, Ozone and Second Life. Empirical model. So in this work, we focus on four mobility characteristics. The first one is pause duration, how long an avatar pause in a waypoint. The second property we look at is the velocity, how fast an avatar moves. And also the third one is the area popularity, how popular the area it is. And the second, the final one is the number of reach areas for the simulate duration. We model each property separately against different statistical models using maximum likelihood estimation, and after get the parameters for different statistics, we evaluate the goodness of fit using two statistical test measures. Yeah. Here I only show the empirical modeling result. The left part shows the result for the pause duration, and the right part shows the result for the velocity. And the red line is the original data, and the black line is the original data, while the red line is the fixed distribution. In this one, I use the plot the result for the normal distribution. As we can see that the fixed distribution in the very beginning is slightly higher. The pause duration is slightly higher than real data, but in general, it's reasonably well. And yeah, as you can see that from the right part of the figure that the fixed pause duration, the fixed velocity is reasonably well with the empirical data. And here is also for the results for the area popularity and number of beach areas. The red line fit closely to the empirical data. Yeah. Then I will introduce SumOver. So SumOver is an area-based mobility model for virtual environments. It consists of two parts. First part is the map generation, how to generate such kind of map. The second part is working path, how avatar moves. the map generation part consists how to generate waypoint distributes according to the map. And then we will generate paths to connect these different waypoints. For the path generation, firstly we will determine the number of waypoints this avatar can visit. Then we will decide how does each avatar to pick which waypoint to go and how to go there. Here's an example of what will work on map. But although it's slightly updated, but the main structure is still there. So as you can see, the workflow class consists of two main content and then two smaller islands and the other smaller island too. Two bigger island and then the other small island too. If you want to travel from the one not that popular area from the west to the east, you need to go to some important cities and then take some road through that. And next, we will zoom in to look at the territorial alliance. As you can see, there's different traffic network connecting different cities. If we want to go from smaller cities, for example, from here to for the city to the north, it's highly possible. If first you need to get to more popular cities, get the traffic. May use all the transportation there, and then go to the faraway cities. So as we can see that the traffic network or the world clock is hierarchy. It's reasonable example for the real world cases when you want to travel some smaller cities to another small cities in other side of the world. It's highly possible. First, you need to go to some bigger cities, and then you will fly to travel there, and then take a train, and then bus, probably like this. Yeah. The map generation for Samba. Firstly, we generate different waypoints across the map. So how we do this? So we partition the map into different rectangular areas, and we pick the central point of the areas as the waypoint. And then we assign a normal distribute weight to each waypoint. As we can see that the different waypoints are different weight, and then in each graph, bigger waypoints imply that the waypoint has bigger weight. And then we assign, after we give different waypoint a weight, we assign a level to different waypoints according to its weight, a level. And the level is important to determine the path connection. And then we connect the highest waypoints with each other. Last, we can bring basically we connect. This is kind of resemble to the real world cases that most of the big cities in the world are really have dynamic life. And then next, we connect each waypoint with its closest waypoints of higher level. This resembles that this kind of smaller around cities always connect to these bigger central cities. And then we connect each same level waypoint with each other if they are connected to the same high level waypoints. After this, we connect waypoints with each other if the distance are smaller than some threshold values. Here is an example of our generate passes. As we can see that if you want to travel from this kind of remote area, first you need to go to somewhere in this big spot, and then through this waypoint we will go to here, and then go to here. So it does not. Firstly, all the waypoints you can travel from any waypoint to any waypoints in this map, but you need to follow some restrict passes. Instead of randomly, you can randomly directly go from here to here in a straight line. Yeah. After we determine how the map is generated, we determine how an avatar can move. So firstly, we assign each avatar a limited number of waypoints it can visit during the simulation. Okay, sample from a normal distribution. And then we assign a start waypoints to each avatar. We use two methods to assign the start waypoints. Someone U basically we assign the start waypoints randomly, and someone W we assign the waypoint according to the weight we assign in the map generation procedure. And then for each avatar, we iteratively add the waypoints, never fully to the already assigned waypoints. This we can make sure that the avatar can always to travel to its visit or to its assigned waypoints. Yeah, here's an example of working path. So here different hatch area represent different waypoints or the avatar can visit. For this blue avatar, it can only visit the blue rectangular areas. And yeah, here's an example. And how the avatar works. First, each avatar will select the next waypoint to go. And based on the personal preference way. Currently, we only assign this kind of personal way to its visit waypoints according to Zip distribution. And this avatar will go to the waypoint using a sample velocity as we introduced previously in the empirical modeling session. And the avatar will work to its select waypoints according to the sorted path. So in this map, when this avatar will travel to here, from one point to another point, it will only use its subgraph to check. Only use sorted path on the sub map instead of the full map. Yeah. Once the avatar arrives on the waypoints, the avatar will pause for pause duration. Here is an example of how avatar travels. When avatar will travel from waypoint A to waypoint E, you will firstly go to the waypoint B, and then go to waypoint C, and then go to waypoint D, instead of directly go left. Validation. As we have already modeled the mobility traces. We have already modeled the mobility properties using the empirical modeling. So besides modeling this property, we also validate whether our model is valid or not using a reference values, number of messages set during the simulation. So in this simulation, we use client-server architecture to simulate that kind of MVEs. So each avatar will, in this simple simulation scenario, each avatar will receive all the avatar's update positions within its area of interest. Area of interest basically is circular areas around the avatar, and then the avatar is in the center of the raw circle. So in this work, we do not use any optimizations. We do not use that mechanism. And in order to, we also compare the journey traces against the real traces. So for a fair comparison, because our model our model do not model the session time of each avatars. We directly use the session time of each avatar for the real traces, and then we compare with the real traces. Besides comparing our models against the real traces, we also use two of the other models widely used in the MVE evaluations. One is hotspot model. Basically, another one is random waypoint model. In the random waypoint model, each avatar will randomly select some waypoints in the map and then directly go to that waypoint. And for the hotspot models, each waypoint has its weight, and then the higher weight the waypoint is, the higher probability the avatar will go to that waypoint. And we saw the normalized the metric count for each simulation. Well, here we normalize the metric count with the real value with the metric count obtained by using the real traces. As we can see, the result of the sum over and the sum over U and W are plotted as the blue line and the pink line here. As we can see that the result for and left part shows the result for iron and right part shows the result for gravy second line. And as we can see that the sum over curve is follow very close to the 1, which means that the result produced by our model is follow very closely to the real traces. And compared to the other models, compared to the widely used models in MVE evaluations, our model is much better than that. You can see see that the model can be twice higher than the real traces, while our model is like kind of between 1.1 to 1.2. So our result produced by model is very close to real traces. And the result also apply to the secondary traces. But for secondary, if the number alpha is small, our result is slightly not that good compared to the work graph data because the map on second line is smaller than the work graph, and also because we mainly develop our model based on the observation from work graph. But still, the result is much better than the result produced by hotspot model and then the waypoint model. So this result means that some of us can produce very close. But in terms of number of messages sent, some of the result of some of us is very close to real traces. Next, I will talk about the limitation of this model. Our model does not model the distance between hotspots. So you can see from our previous slides that if you simply look at it, it's not that realistic of the distribution of hotspot, especially compared to the real scenarios or any game scenarios. We don't have this kind of, we do not have such kind of plaza-like structure or any structure, but we only model the probability, but do not model the distance between different hotspots. And also we do not model the session time. Session time is how long avatar stay in the game world and then they log out. And we only validate with 2 games, and also validate in the Siqi scenarios. And also we only evaluate in client-server architecture without any optimization. It may turn out that our result is different if we apply any optimization technique. But yeah, that's the future. Yeah. Here's some what I will share to you. All models are long, but some are useful. So I hope that our model is sort of useful. Conclusion is that some of our cases, model can produce realistic traces. Thanks for your attention. Any questions, comments, suggestions?
So, any questions, any comments about if the model is too wrong or if there are any improvements can be made to the model? Karsten.
I just have this question. Is there this problem that we have with figuring out if a trace is realistic, that must exist in other fields as well? Is there anybody who has figured out a metric for comparing the realism of artificial traces to real-world traces of that complexity as we have it in games? Has any other field figured that out?
Anyone here?
In this world, we only look at this kind of properties we model, and then we only look at number of messages sent. But yeah, I think there should be more.
Right. But I mean, your last slide shows it all, right? How bad does it have to be before it's no longer useful?
I hope that it's useful, but I don't know.
Is there anybody who figured out how to prove that? Anywhere? In any field?
Yeah, as far as I know, as far as I know from the previous research that many people only focus on the networking on this kind of NVIDIA architectures, and that of course they look at the number of messages sent. But if we want to look at whether it's load balancing and computation power, and then probably another metric should be used. But I don't know, or area predicting or something. And also, if we want to go into another step, whether this kind of we want to simulate more complex NVIDIA scenarios such as fighting, and then I guess another metric should be used. But it's kind of hard to say that which metric can be really used or not, because such kind of data is very difficult to get from the client side. Only if you cooperate with the company, and then hopefully you can get some data.
But it seems that there is some scope to for people to do work on evaluate or developing a metric which can be used to develop it too.
All right, hopefully better than image quality metrics.
Yeah.
Yeah, actually, I think that for the traces, depending what you intend to do with your simulation. If you are going to study sociology, for example, I mean, maybe simulated users are not very useful. But if you want to measure some technical points, I mean, scalability, for instance, it would be useful. So it depends on what you are using the simulation for.
Oh yeah, I mean, I have no criticism about using this, right? I just wonder, do we have any way of figuring out if the competing versions get better or not? Is there any...
depending on what you are doing, this is my answer. Depending on what you intend to do with the simulation. If you want to use study the user's behavior, maybe a simulation is totally useless. But if not, depending on if you want to measure scalability, it could be useful.
I see what you mean.
Yeah.
Just one more question.
Yeah, actually, I was about asking one question in the slide, but it seems that.
Okay,
Sorry.
Okay, it's about the distribution fitting model that you used in one of your slides when you said about looking
data
at
fitting, statistic fitting.
And I mean, by looking at how the curve fits and then how distribution fits, I think that the Kolmogorov goodness of fit test that you use can never really give accurate values, because it seems that the first interval in the x-axis does not fit well at your curve. You see.
Yeah.
So I guess that you may use kind of two kind of distribution to really fit your distribution. You see. So this might be one solution, and this might give some accuracy to your model.
Yeah, so the one of problems of fitting such kind of large data set is that because previously all these kind of statistical models is developed by statistics, they are basically on very small sample data set, small size of data set, like tens or thousands. But when we want to apply such kind of to internet scenario, that we have very large data set. So
yeah.
what we use is this kind of technique is not developed by me. So also it's also used by the other distributed system researchers. So this keep instead of using this kind of okay, it's not exactly the goodness of fit already developed. It's kind of slightly modified version of this kind of goodness of fit. Well, anyway, the more details you can look at our paper. But yeah, you are right that it's not that perfect fit.
Okay, but I think we're going to take this during the break. We can discuss this further. So thank you very much, Siqi. And